Okay, so welcome to the One World Mathematical Physics Seminar. This is a seminar organized by by the International Association of Mathematical Physics and takes place online twice per month. So today we have the honor to have Stephan De Bièvre, I'm sorry, from the Université de Lille, and he's going to talk about assessing non-classical features of optical field states, the many merits of the quadrature coherence scale. So thank you very much.
Well, thank you very much for the invitation in this nice seminar series that I don't attend as often as I would like to, but then I go look at the recording sometimes afterwards. So it's a very nice initiative. So yeah, I'll try to explain my title in the course of my talk, of course, and there's two words at least that need clarification. One is the word non-classical. I'll start with that. And of course, the other is the quadrature coherence scale. So there we go. Okay, so when you use the word non-classical and classical, and when talking about quantum mechanics, you have to be very careful because people can get very upset at you sometimes because the words may have very different meanings to different people or just in different situations. So this is sort of a list of keywords. I think if you ask 100 physicists to you give them one word they can say or two words they can say that are essential in determining the difference between classical and quantum mechanics. I think you will see this list of words mostly. I've tried this in several circumstances, and people don't come up with much else. So there's the uncertainty principle, of course, the notion of incompatible observables, entanglement, non-locality, the collapse of the wave function, and then no hidden variables, contextuality, the Pauli principle. These things come certainly forward when you talk about non-classicality. But if you talk to people doing quantum optics, there's a very precise thing. They talk about optically non-classical states. And this has a precise definition, and I will give it in a second. So throughout this talk, when I say non-classical, I will mean optically non-classical in that sense. And I'll try to stick to that throughout. So concerning the quadrature coherence scale, I will have an occasion to define it properly in a few minutes. But I wrote a series of articles on that subject. I introduced it in the first paper there with some colleagues from the physics department here in Lille who walked into my office and asked me some questions. And so this ended up with this first paper. And then I had a postdoc, Anaël Hertz, with whom I worked some more on this. Then with Nicolas Serre from Brussels. And then with Celia Griffith and Matthew Arnhem, also from Brussels, and finally again with Anaël. So this is sort of the work that we have done in the last 5 years or so on this subject. And as you can see, the papers are published in physics journals. So it's more, as you will see, the talk is sort of a theoretical physics talk, but there is a fair amount of mathematics, and I hope everybody will find something to find of interest. So this is what the talk is based on. Now, so quantum optics, this is a crash course in quantum optics, very short. Of course, the electromagnetic field, there is the E field and the B field, and some boundary conditions, the Maxwell equations. Under the right circumstances, you can express everything in terms of the vector potential, which you can write out in the way I did there. And then if you do classical field theory, classical electromagnetic fields, these AKs and A dagger Ks that appear there are just complex numbers. And if you do quantum field theory, they become operators and they obey the standard canonical commutation relations that I wrote out there. So in that case, the density states are given by density matrix on the appropriate Fock space, which is generated by the action of the creation operators on the vacuum. And quantum dynamics reduces to unitary maps on this Hilbert space. And so there's a large part of quantum optics that reduces, in fact, to the study of various unitaries that model mirrors, beam splitters, phase shifters, and other equipment that you find in quantum optics labs acting on a Fock space. And so much of it actually doesn't go back to explicitly studying the behavior of the field itself. So with that in mind, I can start by giving the precise definition I referred to before of what it is to be a classical state for a bosonic field. And so this is a purely mathematical thing. It's all written on this slide. So you just have L2 of Rn. So on Rn, you have, of course, the position and momentum operators. There is n of them, right? Xk are the components of the position operator and Pk of the momentum operator. In quantum optics, these things are referred to as quadratures. Then you can define for every complex vector in Cn the corresponding creation and annihilation operators, which I wrote down there, and the displacement operator, which in the mathematical physics community we usually refer to as the while operator, which is given by this exponential that's written in the middle of my slide right here, and which is, of course, a unitary operator. And then you define coherent states in this manner here. You first have the vacuum state, which is just the ground state of the harmonic oscillator. This should have been an x squared here rather than a q squared. And then the coherent states are obtained by applying the while operators or the displacement operators to the vacuum. And of course, they satisfy this well-known property that they are eigenvectors of the destruction operators or the annihilation operators. So this is, of course, a framework everybody is very familiar with, if not from quantum optics, then from just harmonic systems in general. And there's a definition that goes back to Glauber and Titular in 1963, and it goes, as you can read there, it says that the positive operator is optically classical. I will say P positive later, but it's optically classical if there exists a probability measure so that it can be written as this. So this, of course, it's easy to paraphrase and better to paraphrase it. A classical state is a mixture of coherent states in one line. And it's best to remember just that. What is a classical state? Well, it's a mixture of coherent states, period. And so that's what's written here in full glory. So this P is because everybody calls it the P-function. So I write P alpha D alpha, but you could just see this as a measure. So what you need is a probability measure. You can think of a probability measure here, and what you say is that if rho hat can be written like this in terms of some probability measure, then you say that the operator rho hat, the state rho hat, is optically classical. And I write, I will often say P positive because it avoids the word classical precisely. You just say P positive, that's a neutral thing to say. Nobody can get upset at you for calling this classical. So this is a set of operators, a subset of the set of all density matrices. It's not more. And it's, of course, a convex set. And so the question is how you characterize that set. And of course, you can say, but you just characterized it because you gave a definition. Okay, but the question is, if I give you, in some manner, a density matrix, how do you decide that it is or is not in that set? Okay, so this is, okay. And when I say if I give you a density matrix, you can wonder what that means, right? Do I give some matrix elements in some basis or do I give some other information? Anyway, I can also define it as a solution of some evolution equation, and then I've given it to you. But you have to decide then, given this density matrix, if it is or is not in this set. And that's not an easy task. So I have sort of an artist's rendering here of the state space. Of course, as you can imagine, this oval thing here is the set of all states with on the edge of the pure states. These are the pure states there. And then here, the brown ones here on the edge are the coherent states, these things. Then if I take the convex hull of those, I get this region here, this little piece of cut off from the oval, which are then the classical states. Okay, that's the definition. They're mixtures of coherent states. But there's here, the blue guys here, they're pure states because they're on the edge, but they're Gaussian and they're not coherent. There exist Gaussian states that are pure and not coherent. Okay, so these are the blue guys, and there's some there too. You can also look at the convex hull of the Gaussian states, which is this blue region here. of the Gaussian pure states, if you wish. That doesn't have a name. It's a bit annoying because it'd be nice if you had a name, but this is just the convex hull of all pure Gaussian states. It contains the Gaussian states, which is the pink region here. The pink region, and I draw this jagged line to make it clear that it is not a convex set. If you take a mixture of two Gaussian states, you don't get a Gaussian state, of course, in general. So the blue region is the set of all Gaussian states. It is contained obviously in the convex hull of all Gaussian states, which contains the classical states, etc. So this region we understand. Then there is something called the Wigner-positive states. I'll say more about the Wigner function, but I think everybody knows what it is. So the Wigner function is some quasi-probability distribution associated to each state, and it is a real valued function, and it can be positive everywhere or not positive everywhere. The states for which it is positive everywhere are make up this green region, plus all of this, right? These are the... So of course, well, we'll see, but all of these, all Gaussian states have a positive Wigner function, and so they're mixtures too. And so this blue region certainly has positive Wigner functions, but there are positive Wigner functions, or states with a positive Wigner function that do not come from Gaussian states as well. And then you have states that are here that have that are Wigner negative, as people say. They have some negativity in their Wigner function. So this is sort of a picture of all states, if you will. And so if I give you a state rho, you can try to decide whether it is here, there, or there. Okay, and so yeah, and so this is what I'll be talking about. Okay, so let's try to do this for a few states. Let's benchmark this problem a little bit to see when it is easy, when it's not easy, how you go about this, and what the problem is. So the case of pure states tends to be easy. We were not surprised, right? So, for example, the only classical pure states are the coherent states. Of course, if you look at the definition, where is it? No. Where's the definition? Here. If you make if you do something like this, as soon as this measure is not concentrated on one point, the state is not pure. So the only way to have a pure classical state is to have a coherent state. So that's easy. I promise it was easy. It's easy. So the only classical pure states are coherent states. For Wigner positivity, it's not quite so easy, but it's been known for a long time. It's a result by Hudson in 1974 or something. He proves that the only Wigner positive pure states are the Gaussian states. And this is correctly represented here, because you see my green set of pure states, it hits the boundary exactly where the Gaussian states end. Okay, there are no pure Wigner positive states that are not Gaussian. Okay, that's why I draw this thing here, hitting the boundary just right there. Okay, so this is an old result. I'm sure many of you know that. So that's the case of pure states. Let's have a look at the liquid Wigner positivity. So of course I showed it to you on this picture, but let me say a few things about it. So first of all, let me remind you what the Wigner function is. So the easy way I find to define it is to define the characteristic function of the state, which is just trace rho d psi. Remember, d psi is the displacement operator or the while operator. This gives you a function, a complex valued function, called the characteristic function of the state, usually. And the Wigner function is nothing but the Fourier transform of that. And of course, there's some convention with the minus sign, but it's basically just the Fourier transform. The Wigner function is the Fourier transform of the characteristic function. Okay. And then there is this result here, which is very simple. If rho is a classical state, if it has a positive P function, then it also has a positive Wigner function. And it follows from the fact that you can compute the Wigner function from the P function by simple convolution with the Gaussian. And so this is also known for a long time. So these three statements is 3 times the same thing. I frame this one because it's easy to remember. P positive implies Wigner positive. And then classical states have positive Wigner functions. When there's an S too many there. that's just a rephrasing of the same thing, and this is again a rephrasing of the same observation. And of course, the converse is false. There exist Wigner-positive states that are not P-positive, which again, I try to evoke in my, there exist, what did I say, Wigner-positive states, what did I say, that are not P-positive, right? So these are sometimes called generally, yeah, the ones that are not in the convex hull of the Gaussians are sometimes called generally non-Gaussian. I don't like that terminology, but that's what people call it. Some people even call it quantum non-Gaussian, which I understand even less as a terminology. But it means not in the convex hull of the Gaussians. Okay, so this is just some literature. Okay, so what else do I have here? Yeah, let's have a look at Gaussian states and their P-positivity. Again, the picture showed it, but let's put some definitions down and a lemma or two. So I'll recall what a Gaussian state is. State is Gaussian if its characteristic function is Gaussian, which is written here quite explicitly, and it is expressed in terms of the covariance matrix of the state, which I wrote here. I think the notations are clear. These are the expected values of these different operators in the state rho. That's what I call the covariance matrix. And you stick that up there, and then you get the characteristic function. This is a Gaussian, obviously. And so, of course, Gaussian states are Wigner-positive, because to get the Wigner function, you have to Fourier transform this. And this is a Gaussian, so it's again a Fourier transform, and so it's positive. So that Gaussian states are Wigner-positive is obvious. That's what's written there. But it's not true that all Gaussian states are P-positive. Okay, and there is a result that's old also, you find in the literature. It says that a Gaussian state is classical if and only if the covariance matrix has this property here. It's bigger than the unit matrix. Okay, so this, again, it's not very hard to prove, but it takes a little bit of work to prove that. So Gaussian states, some of them are P-positive and others are not. Okay, which was visible, I hope, in my drawing. So these Gaussian states are not P-positive, and these ones are. Okay, or these ones are. Sorry, these ones are. So okay, so that's that. And then here are some examples of both classical and non-classical Gaussian states. The coherent states correspond to a unit matrix for the covariance matrix. Thermal states are also classical. Their covariance matrix looks like this. So this is bigger than 1, right? Because Q is a positive number. Then you have the famous squeezed thermal states. There's a lot of terminology, right? But physicists, there's only certain operators or certain states they either encounter easily in nature or can make more or less easily in their labs. So they give names to the ones they can make, basically. So squeezed thermal states are these guys. So you take a thermal state and you apply this operator S to it on both sides. You get, again, a trace one operator, positive, obviously, and this operator is called the squeezing operator. It just dilates, actually, and it has this form. You know, it's self-adjoint because this thing is, it's unitary because this thing up here is anti-self-adjoint, and it's a quadratic Hamiltonian, if you wish, which preserves Gaussianity. So these are the squeezing operators, and if you look at the covariance matrix of this state, it will look like this. It's a diagonal matrix. And as soon as R is positive, this thing is no. If R is positive enough, you know, there's 1 plus Q or 1 minus Q, or then this is going to be what am I saying? They are not classical. They will be non-classical. They will have they will not have a positive P. So this is sort of a set of benchmarks. And then for non-Gaussian states, you can sort of go look around. For pure states, we said it's quite easy. But for mixed states, you have to work each time. And I'll give some examples later on. Okay, so now we know what I mean by classical states. Now the question is how you recognize such a thing. Okay, so I give you a state, you have to recognize if it is or is not classical. So in general, it is hard to determine the P-function, and in fact, it may not really exist in any reasonable mathematical sense. Because, it is because it's the Fourier transform of something that doesn't necessarily have a decent Fourier transform. So it's not necessarily well defined. And so you need simple criteria that you would like to be computable and measurable in the sense of being able to measure it in a lab to determine if your state is or is not optically non-classical. So the two questions you are asking is it or is it not non-classical? And once it is, how strongly is it so? Right? Because there is this, you can say, it's like with entanglement, you can say this state is entangled and this one is too, but which one is more entangled? It's not enough to have a witness, as people say, that tells you, yes, it's entangled, no, it's not entangled. You also need to be able to take two states and decide which one is more entangled. You need some criteria. And of course, you can fight about what the good criterion is. Okay. And it's the same here. So this problem goes back to the 1960s. I showed you the definition, right? So it goes back to 1963. And there was a lot of work in the early days of quantum optics. And then it sort of petered out a bit. And then with the arrival of quantum information theory, there was a revival of interest. Because to make it short, you can't get a quantum advantage if you don't have positive, if you don't have non-positivity, if you don't have negativity. That's sort of a rule to think of it. Depends what you want to do, but in general, you need some kind of non-positivity to get a quantum advantage. Okay, and so that's why people keep coming up with ways to decide whether states are Wigner negative or not, P negative or not, etc. Quantum non-Gaussian or not. There's all these sets that people describe, and then they try to find out if a given state is in it or not. So how you go about this, with witnesses, I already used the word. So a witness is some function you can compute on your states, and that there is a threshold somehow. And if you're below, you know the state is non-classical. If you're above, it is not. You don't know usually. There is, unless the witness is faithful. So here's the first example, the famous one that goes back to Mandel, 1979. It just, these are just moments, right? You take the state rho and you compute these moments that are up there, fourth order moment. Is this? Yes. Divided by another moment there, which is actually the mean photon number. And if this thing is negative, so it actually is the top, then the state is non-classical. That's not too surprising because you have some kind of variance here. Modulo commutation relations, but this looks like a variance a little bit. Right? If everybody commuted, this would be a variance. And so if this thing is negative, then indeed the state is non-classical. Whereas if it's positive, it can be classical or non-classical. It's not a faithful witness because it's like what we teach our students about conversions of series, right? You have some criterion and then it works sometimes, but not always. There are many variations on this. So this computes certain moments. There's something called the moment method developed originally by Agarwal and Zara, and then developed much further by many, including recently by Arnhem, Serre, and Griffith. To just give you an idea, these are recent papers. So this is a line of thinking that has developed considerably since. There's also other ways to go by use of the Bochner theorem. There's also a literature on this for the last 20 years or so. You can use also other moments than those here. This involves, you see, this is again the square of A plus A dagger, but there's an angle there, phi, and you can play on this angle to figure out if your state is or is not non-classical. So this is generally, I call this moment methods, basically. So this is the first set of things you can do. Then you can also use the Wigner function because, as I said in my diagram, if your Wigner function has negativity somewhere, then you're sure that the state is not classical because you could see that on the picture, right? Here, right? If you know that your state is in here, well, then it's certainly not in there, right? So Wigner negativity implies P negativity for the simple reason that P positivity implies Wigner positivity. So I was, where was I? This I said, no, did I? Yes, did I say? Yes, I was here. So this is the moment method. You can use negativity. And so this is again the definition. I gave it already. And there is also many variations on this, including recently. I just gave some reference. So the problem with, of course, all these witnesses is that these tests fail for many non-classical states. For example, if you're going to use Wigner negativity, you'll never detect the non-classicality of a Gaussian state because they all have positive Wigner functions. And similarly, it won't work very well for photon added or subtracted Gaussian states for similar reasons. And the second reason is that these things are on-off, they're witnesses, but they don't provide you with a measure of non-classicality. It's not because the moment here is very large and negative that you can claim that the state is very non-classical. There is no real link between the degree of non-classicality and the value of this witness. So these are the two problems that many of these witnesses have. And so people come up with the question, what can I use as a measure? And so a very famous one and popular one is the one to just, you compute simply the integral of the absolute value of the Wigner function. Now this is basically the volume below, the volume of the negative part of the Wigner function. Because the Wigner function itself has an integral which is 1. So if it goes negative somewhere, you will pick up how big the part is that is negative, and that's what's called the negativity. It's the volume under the graph. Okay? And so W0 is just W, that's just the Wigner function. There's some other proposal, but this is something that's very often used. Then there's another set of things people do. It's obvious, right? If you have a set, a subset of the set of all states, the natural thing to do is if you have another state to compute the distance. If the distance is strictly positive, you know you're outside. If the distance is 0, you're inside. But then, of course, you're in infinite dimensions, so there is many distances to choose from. And so, yeah, okay, so you have an infinite dimensional set, a set of all states, and then you have a subset, and you come up with some distance function, and then you define you define the non-classicality, if you wish, as the distance between the state and the set of classical states, the given state and the set of classical states. And then you say the bigger this distance is, the more non-classical my state is. You can do that. But of course, this is arbitrary for obvious reasons. There is a choice to be made for this distance. And people have tried various things. And the problem is that usually there is no clear interpretation of what these distances mean. On top of that, they're impossible to compute. I mean, even in finite dimension, computing the distance from a point to a given but complicated convex set is not necessarily an easy task. So in infinite dimension, it is not something you can compute. Okay. So you have witnesses, you have these measures, the negativity or some distance-based measures, and they all have their issues. So now, what is a good, we can do it this way. What is a good non-classicality witness? Well, it should have the following properties, ideally. Ideally, of course, it should be faithful. It should be on-off. If you compute something, if it is bigger than 0, you say it's not in the set. If it's less than 0, it is in the set, or the other way around. It should provide not only an on-off thing like that, but it should provide you a measure also. It should tell you how non-classical your state is. It should be easy to compute, either analytically or numerically, on large families of states. It should also have a clear and hopefully exciting physical meaning. It's not enough that you have some quantity that maybe you can compute, but you don't know what it means. So you need it to have some interpretation. And better yet, it should be easy to measure in any quality optics laboratory near you. So you should be able to go to your friend quantum optician and tell him, listen, I found this thing here, measure it. And then that's the last thing. It should be what people like to call a figure of merit. So you should have some task in mind that, and now I have two states, this one and that one. Okay, and this one has a higher non-classicality than that one, but this one should be better at doing something than that one. And I should be able to say, with this one, you can do that thing better than with the other one. You should have some protocol that works better with one than the other. This is where you come into quantum advantage, right? I mean, so this is sort of the wish list you can send to St. Nicholas here in Flanders, anyway, or to what's the figure at Christmas? I can't find his name anymore. Father Christmas, right? You send him this wish list, and you said, "I want a measure of a witness of non-classicality that does all of this." So again, here it is. Okay, now I'm exaggerating. I will tell you the many merits of this quadrature coherence scale, which I'm trying to, this is a sales pitch, okay? So I'm going to try to convince you that many of these things are done by the quadrature coherence scale. So I first have to define it, and then I have to go through this list here and tell you which of these features are indeed features of this quadrature coherence scale. So, okay, so you can, this is just a mathematics slide here. I do everything with one mode, meaning I'm in L2 of R to limit the notations, to make the notation simple, but it all works for higher, for many modes too. So I have a one mode field, which I have X and P, A and A dagger on L2 of R. That's it. I have the vacuum, of course. I don't even, yeah, yes, okay. And I define this object there. So let's look at it. It's 1 over 2p. The p here is the purity. It's written there. It's the trace of rho hat squared. So 1 over 2 the purity, and then there is this thing. So you take the commutator of x with rho hat, and you basically square it. And then you take the commutator of rho hat with p, and you square it, and you add these two things. Now already there you can start saying, what does this mean? Well, this commutator is sort of the speed at which rho changes if I try to translate it, right? That's one you can say, right? Because this is the derivative. This is the derivative, right? So it's like shifting rho by e to the I ax a little bit and looking how fast it changes. And the same thing with e to the I ap. So this is sort of the sensitivity of the state with respect to translations in phase space, measured in, well, basically in the Hilbert-Schmidt norm. That's one thing you can say. So you can write that down, very easy. There it is. If you write that out a little bit, what I mean by rho hat xx prime is just the kernel of the density matrix in the x basis, meaning the eigenbasis of x here. So in the direct space, basically. And the same here in the momentum, in the conjugate basis. And if you write that out, you get this. The purity is still sitting there. And if you look at this, well, it looks like a variance, really, right? And I'll say it's written down here. It measures how far from the diagonal rho hat xx prime lives. If rho hat xx prime was diagonal, meaning sort of a delta function, then this thing would be 0. Right? And the same on this side. So I like to paraphrase it the way I wrote it in purple here. What does this thing measure? It measures the width of the strip where this thing lives, squared, plus the same thing for the other one. Okay, and I'll show you pictures. So as you know, certainly these matrix elements are often referred to as coherences when x is different from x prime. People will say these are the x coherences of the state rho hat. Okay, so it measures the width of the strip where the x coherences live, plus the same thing for the p coherences. And I take an average of these two. So it has an immediate interpretation. Okay. And so it means that if this thing is large, then my state rho hat must have either x or p coherences far from the diagonal, otherwise this thing cannot be large. And if this thing is small, both of them must live close to the diagonal. So so this is a formula. This is one way to rewrite it, and this is the interpretation, or a first interpretation, I should say. So I like to say that the quadrature coherence scale, QCS, is a coherence locator. It tells you where it is. Now, many people write quantities that measure how much coherence there is. This is not doing that. It says you where the coherence is. It doesn't measure how much there is, but where it is. Okay? Okay, so that's the definition. Now, here's some examples. So what's plotted here is not the Wigner function, of course. There's an x there and an x prime there. It's very small, but so here's the plot of this kernel for a thing people call the cat state. It is a superposition, not a mixture, a superposition of a coherent state and alpha plus minus alpha. Very often A and minus A. So if you think a second, you understand that it must look like that, because you will have a term that comes from alpha x. You get a term from the diagonal term, and then you get off-diagonal terms, so you get these two things and these two things. Okay, that's what rho x prime looks like. And so if I asked you to guess what the quadrature coherence scale would look like, you would sort of have to calculate the distance between these two blobs, and you would come up with something not very far from 4. So this thing has a quadrature coherence scale which is about 4. Now this is the Fock state, meaning the number state with n equal 4. This one is written here, right? Just the fourth eigenstate of the number operator, or the fifth one if you wish, n equal 4. For this one you can compute it explicitly. You find it is 3. And yeah, if you look at rho x prime, you get some slightly more messy thing, because of course, if you put n equal 4, you get some polynomial times a Gaussian, and these are, you see the fluctuations in this polynomial. But the width of this strip, if you were looking closely at the picture, you would see 3.5 is there, right? And 3, it's around 3 sort of, right? The size of this thing, diagonal. And so indeed, it's 3. Okay. So you can just look at these screens and immediately know what the quadrature coherence scale would be, more or less, without even computing it. Okay. So these are some mixed states. These were two pure states. These are mixed states. And this is a thermal state. Now you can see me coming. The quadrature coherence scale of the thermal state is very small, because there are no coherences outside of the diagonal, basically. And indeed, it is, what is it? 0.3 for this thermal state. This is a thermal state for which the mean photon number is 5. And on the other side, they have some non-Gaussian state, which is written explicitly there, but it doesn't really matter. It has also mean photon number 5, and it looks like this, the graph of rho hat x prime. And again, the quadrature coherence scale, and no, sorry, this time the quadrature coherence scale is large because there is this long strip here away from the diagonal, and so it is about 10 times larger, actually. Okay, so you can just look at these things and immediately know what the quadrature coherence scale is, more or less. Okay.
Yeah, Stefan,
yes.
Don't you have to look at rho p prime in these cases?
Yes, but you will find the same thing in these cases.
Oh. Mm-hmm.
Because they're all they're all spherically symmetric, actually. Mm-hmm. In these examples. So yes, you have to look at both, but you will find the same kind of picture, and so the average will be the same as well.
Okay. Mm-hmm.
Okay, but you're right, absolutely. Thanks for the question. Okay, so to convince you further that you can compute this thing, here are some explicit expressions. So actually, for pure states, it's actually quite boring, because it reduces to the variance, the sum of the variances. So this expression here, which looks reasonably fancy, maybe, if you stick a pure state in there and you compute 2 lines, you end up with this. So in fact, this quadrature coherence scale restricted to the pure states is just the sum of the variances of the x and the p quadrature. So it's an extension from that inside the full set of mixtures of mixed states, which doesn't coincide with that any longer on mixed states. But on pure states, it coincides with that. As a result, for number states, it's equal to that. For Gaussian states, mixed or not, you can compute it very easily, because it's expressed directly in terms of the variance. So again, it's probably not too hard to believe if you try to compute this for a Gaussian state, you're going to be able to do it, right? Basically, you can compute anything with a Gaussian state. So I'll show you how you do it afterwards. But if you stick a Gaussian state in there and you look at it for a while, you come up with this formula where V, remember, is the covariance matrix. So it's enough to know the covariance matrix in that case to compute the quantity. For non-Gaussian state, it becomes much more difficult. I know these are some examples of non-Gaussian states that are popular in the literature. These are called photon-added states. Photon-added means that you multiply with A dag on one side and with A on the other. This is the squeezed thermal state I had before. You do that. This can be done in the lab under certain circumstances. And in fact, if you take your squeezed thermal state to be just the vacuum, meaning that it is not squeezed and not thermal because it's just the ground state, then you just get the first you get just the first Fock state, right? So these things are called photon-added squeezed thermal states. And for these things, you can compute this quantity. Now it is explicit, but it's actually quite a mess. And so there is an explicit. It's simple if you expand it, for example, for small q and r. So you can get explicit expressions. And here's a graph of the thing. And what you should see, for example, on this axis, I have a Q, which is the temperature, basically, right? Here, when Q is 0, I'm in the vacuum state. When Q goes up, I increase the temperature. I get more noise, if you wish. And if on the vertical axis, I have R. It's a little small, but it's written there. The vertical axis, I have R. And as I go up, I squeeze more. I have this parameter R gets bigger. And if you look at the scale here, it goes from, let's say, from 0 to 80. It goes up very fast. So the quadrature coherence scale grows very fast. For example, if you increase squeezing, it tends to decrease with temperature, which is going in the right direction because I'm telling you this thing, I'm telling you what it does. But my title says I'm going to talk about non-classicality, and I have not made the link between this object and non-classicality, but that's coming, of course. So the quadrature coherence scale, you can see here, it goes very fast up there. If you compare that to the Wigner negativity, it actually doesn't move very much. It is maximal here, and it's not very sensitive to squeezing, actually goes down with squeezing a little bit, with squeezing, yes. So this is to convince you that this thing can be interpreted and computed. Now, what is the link with non-classicality? This is the title of my talk, right? Let me look at my clock here. Ah, yes, I have to move on. Okay, so here's a theorem. So I rewrote the thing with all bells and whistles to make sure you believe me that this is can be made rigorous, what I'm saying. So I introduced this space here. LHS means the Hilbert-Schmidt operators, okay? And so I take those Hilbert-Schmidt operators whose commutator with X and P is still Hilbert-Schmidt. So this is sort of a domain, the intersection of the domains of two operators, right? I have the operator commutator with X, the commutator operator with P, and my operator A has to be, I mean, if you apply these commutators to A, it must still be a Hilbert-Schmidt operator. So I call this LHS1. The 1 is because it's like one derivative. And then for any AB in this space, I define this thing, which is an inner product. And of course, you recognize my expression for the quadrature coherence scale. It's the same thing, except I put A and B instead of putting rho twice. So this is an inner product, and so I introduce this notation for the norm associated to this inner product, and then it's immediate that the quadrature coherence scale is given by this norm, where I normalized by the trace of rho squared, which was the purity. So this is just a little computation, and this makes it clear that this object is well defined. In particular, because I claim that a set of classical states is contained in this space, and that's the crucial part. If you take a state in there, its quadrature coherence scale will be less than 1. And so that's finally, I'm arrived at the end of my title now. because I have explained to you that the quadrature coherence scale is a witness of non-classicality, because if I'm classical, then my quadrature coherence scale is less than 1. If the state is classical, meaning it is in this set here, then its quadrature coherence scale is less than 1. So this object I introduced, which seemed to have something to do with coherences, is actually linked to this notion of classical. Okay? Okay, and then you can do a little better because it is not faithful, but you can introduce a distance using, since you have, you have an inner product on a space, so you can introduce a distance. So if you introduce this distance, then now you have a distance measure, which is written here. You take the infimum over all states that are classical. You take rho tilde minus sigma tilde, you call that the distance. And it turns out that this distance is bounded above and below by the non-classicality. Now, this distance is impossible to compute because you have to take this infimum over this set that you don't know very well. But it doesn't matter because if the non-classicality is large, it's basically equal to the distance. You know, there's an upper and a lower bound. So if C of rho is very large, then basically this distance is equal to the QCS. And so this gets you into the idea that not only do you have a witness, but you actually have a measure of non-classicality. Okay? And so this is what I wrote down here. So like other distances, this distance is not easy to compute, but the quadrature coherence scale is, or at least for many, many cases. And so that's a good thing. Okay, so now we have, these are some of the merits. I think I wrote the many merits of the quadrature coherence scale in my title. So I've given you some of the merits, but let's keep going. This is a quick summary of what we said so far. So if the quadrature coherence scale is bigger than 1, you're sure the state is non-classical. So you have a witness. Okay, then I have these things about the distance I just said. These are some details I don't need to go into. But this is interesting too. When I say that it can be computed in many cases, there's many different expressions. For example, if instead of the defining expression, you can rewrite it like that. Here, W is the Wigner function. This is just the gradient, of course. So if you compute the L2 norm of the gradient and you divide it by the L2 norm of the Wigner function, you get also the quadrature coherence scale. So if you look at it this way, then you understand that somehow this thing measures the oscillations in the Wigner function, which is something people again associated with non-classicality. So this sort of falls into place as well. Okay, so more physical interpretation. There's two more things. There's decoherence and entanglement. And I'll try to, I'll take another 5 minutes and then that'll be fine. So there is a sort of a dogma I wrote. That's not a very nice thing to write. There's sort of a general principle I should have written. There is a general principle that people believe is that quantum features of a state are destroyed fast by environmental coupling. The more quantum a state, the more sensitive it is to decoherence. And so strongly non-classical states should decohere quickly. That's sort of a dogma is a bad word, a general principle. And so you would like to think that if this quadrature coherence state has anything to say about non-classicality, it should decrease fast under coupling, under decoherence. And let's see if that's true. Of course, you see me coming. It is true. What we did is in this paper with Anna Hertz is to take our single mode and couple it to a reservoir at some temperature with the Lindblad equation, with the simplest Lindblad equation everybody writes down. And then you can compute the time evolution of this QCS, of this quadrature coherence. And what you find out is that the time rate of change of the time over which the quadrature coherence scale decreases is inversely proportional to its own square. So the larger this thing is, the quicker it decoheres. And the same for the purity loss. So in fact, you can interpret the quadrature coherence scale as the inverse of the inverse of it as a time. And so the larger it is, I like to say, the more you have of it, the quicker you lose it. So it decreases very fast if there's a lot of it, it decreases very fast in this manner. So this again points in the right direction. Then you can say, well, what about entanglement? I mean, you know that all classical states are non-entangled because they are mixtures of coherent states, which are product states. So classical states, in the sense of titular Glauber, are not entangled, they're separable. Okay, so now you would like to think that if some state is very entangled, it should be very non-classical. And so this is what's written here. You would expect that strong entanglement implies strong optical non-classicality. And so we proved something along those lines in a paper with Anna Hertz and Nicolas Serre, and I will just point you here. So this is the simplest case with pure states. You have a system of n modes that you think of a bipartite system. There's NA plus NB modes. To make it simple, we take them equal. It works in general, but so you take a system, you split in two, you have NA modes here and NB equal NA modes there. And you look at the entanglement of formation, which is this quantity everybody knows. I think you take the partial trace. Yeah, you take the partial trace of your state and you obtain rho A, and then you take you compute its von Neumann entropy, which is the same on each side. And then you can prove this. So the entanglement of formation is smaller than the logarithm of the quadrature coherence scale, which means that if you have a lot of entanglement of formation, the quadrature coherence scale must go up, which is what you want. You want something like that. And if you do this for Gaussian states, you get something similar, and it's more interesting because Gaussian states are a bit more complicated. You can do it for mixed states and have computable quantities. So basically, again, you should just look at this thing here. So for this quantity here is the logarithmic negativity, which is a known measure of entanglement for Gaussian states. I didn't write the definition, but just think of it as a measure of entanglement. And what's written here is that if the entanglement of the Gaussian state is large, then C squared must be large. And it's quantitative. You have some, you have some factors there, but basically the quadrature coherence scale grows exponentially with the entanglement, which again is something that reassures you in terms of the notion or the meaning of the object. So I will not do that. So finally, how to measure this thing? Because I said that if you talk to physicists, they will ask you first about the meaning, and then they will ask you, can you measure it? And so when I give talks about this 3 years ago, I would always say, well, of course, yes, you can measure this. You just do a tomography. So, physicists know how to do a tomography that is in optics. It's a lot of work, and then you get all the information about the state rho hat. Okay, fine, and then you can compute anything you want, right? So that's a cheat. I mean, you say, okay, you just do a tomography and then compute it with one of my formula. You can either use the formula in terms of the Wigner function or directly this formula, do something, okay? But people will say, yeah, okay, but that's hard work. I mean, this tomography, you won't get a very precise results. It's not going to work very well. So that's a bad way to measure the QCS. This is the way I would tell people up to 2 years ago. And then we wrote a paper, and I'll just go through it very quickly, that says how you can measure this thing. What you have to do is you take 2 copies of your state and feed them into a beam splitter. 1 copy goes there and 1 copy goes there. This is a beam splitter, and so these are the 2 out modes. And you measure the photon number on one of these out modes. Now, I naively thought, I said, I mean, these quantum optics guys, they've been doing quantum optics for 60 years. Counting photons must be easy, right? It turns out that it's not so easy, but they know more or less how to count photons. So all you have to do is you take 2 copies of your state, you send it into a beam splitter, and on one of the branches of the beam splitter, you measure the photons. And you get a distribution of photon numbers, which I called Pn. It's right there. Pn is the probability of finding n photons on that branch. So it's just a measurement that you do. And then you compute this quantity on the right, it is equal to the quadrature coherence scale. So you do a post-processing, indeed, you don't get the number on your screen, but you get the graph of P as a function of n, and you have the data, P as a function of n, and you compute this object, and you get the quadrature coherence scale. So this is a way to measure it, which looks easy, right? You just 2 copies of the state, 1 beam splitter, and 1 photon counter. Okay, so what does that do? Well, this is a hypothetical measurement. Yeah, so you have Pn as a function of n. Okay, and these are data for 3 different, they are theoretically produced, these guys. Okay, these are data for 3 kinds of states. The first state has a c squared, the red one, c squared equal 13. The other one has c squared equal 1.2, and the third one has c squared equal 0.8. So I could write these states down, but I didn't do it. But just believe me, there are 3 explicit states for which we can compute this, that, and that, and for which we can compute numerically, numerically, these graphs. Now, you immediately see that, you know, there's a difference between the red, the blue, and the green, right? Especially between the red and the green. The green one is smooth, the red one oscillates a lot, and the blue one oscillates a little bit, right? And so, in fact, the quadrature coherence scale manifests itself in the intensity of the oscillations in the photon counting probabilities. And this is not surprising, because if you look at this formula, there is this -1 to the n here. So the more this thing oscillates, this Pn oscillates, this is going to be enhanced by the -1 to the n, and especially by the factor n that sits there. Okay, and so again, if you have an experiment that produces such a graph, you could almost read off, I'm exaggerating a bit, but you could almost read off by just looking at the graph whether your state is very non-classical or not. Because if it is jagged, it is, and if it is smooth, it is not. Okay, now you say, okay, this is just theoretical stuff. This is a protocol we proposed, and now some people did it a year ago. So some experimental physicists in Toronto picked up on this, and they did the experiment and showed that this works. And I will not insist on this. Just my final message is this. So I told you the list of the shopping list for a good non-classicality witness. It has to be faithful, provide a measure, easy to compute, a nice physical meaning, easy to measure, and provide a figure of merit. And so the QCS provides not the first, it's not faithful, but I explained why that doesn't matter. And it does all the other things, but the figure of merit, I'm still looking. And so, well, so this is the end of that. And I think I said all of this, so I will stop right there.
So thank you very much. This was a great talk. So you could unmute yourself so we can clap the speaker. Okay,
I saw people clap, so that's okay.
Ah, good. Okay. So if you want to ask some questions, please unmute yourself and just ask, or you can write in the chat if you have some problem switching on the microphone.
Yes.
Yes.
So is there a simple explanation that why you want to divide everything by the purity when you define this QCS? In your intuitive explanation of this width, I think I didn't see the role of purity in this explanation.
It's a very nice question. Yeah, the quick answer is no. But I can say something nevertheless. Let's see, let's go to the definition here. Here. So indeed, why divide by purity? Well, for one thing, if I didn't divide by purity, I wouldn't have the result. Okay. That's not a very good. That's not a very good answer. I mean, that is a good answer, but there is an answer I like, and I'll try to explain it. I didn't write this down, but if you write the purity out in terms of rho x prime, let me just speak it. I don't have anything to write here. The purity is equal to the integral of modulus rho hat x prime modulus squared dx prime. We agree on that, right?
Yes.
Okay, so if I divide by that, I see that actually this thing here that I'm circling, divided by the purity, is a probability measure on the plane XX prime.
Yes, yes, yes.
And that's, I mean, that's a mathematical explanation, but that's why I'm entitled to say that this is a distance.
The
If I
same
didn't
thing for
divide
P.
by the, say again?
Yeah, the same thing for PP prime.
And the same P for PP prime, yeah. So this is, yeah. Another explanation of the same type really is, so there's an equivalent expression here. This is the same object, okay? And here you say, well, okay, so I said something in the beginning, we have this expression actually. And so at the time I said, okay, this makes sense because it measures the oscillations in the Wigner function. There's a gradient in there, right? But you have to normalize it by something because the oscillations by themselves, and apparently the right way to do it is this. But so that's the two answers I have for you.
Okay, yeah, thank you very much. They are clear, yeah.
Other questions?
I have a question.
Yeah.
Hi. Is this driven by theoreticians or by experimentalists? So do experimentalists really care about various questions that theoreticians investigate, like the one that you presented? Oh, is my, yeah.
Yeah, I understand your question. Let's see. There is vast literature on this, including experimental literature. Now, you said driven. So whether these experimentalists go investigate this because they know they can do it or something, or whether they come up themselves with a question, that's a different one. But it certainly, there's a lot of experimental work on trying to detect whether states are Wigner-positive or not, classical, non-classical or not. There is a lot of experimental work. I mentioned, well, so yeah. And so that's why, yeah, okay.
Do they see, do the experimentalists see that this state behaves differently because it is non-classical in that sense, or do they really care about?
They do. And for example, if you do, it depends on situation. People interested in quantum computing related subjects will tell you that you need negativity to hope to create things that are not classically simulable. So if you want to make circuits that are not classically simulable, and the same way, if you want to make use the quantum, if you want to use photons and optics as a platform, you want to make networks that cannot be easily simulated, you need some form of negativity. Wigner negativity, P negativity, you need some form of negativity. So then people certainly worry about what states. They can easily produce Gaussian states, and they try to figure out what states they have to add to the system to hope to get the quantum advantage. And
thank you.
Yeah, so yes, I mean, yeah, I hope will you be in Strasbourg?
I will.
Good, then we can talk more about that. I'll be happy to explore that further.
So they can actually create non-classical states. I mean,
yes, yeah, of course. I mean,
use them in this computing.
The basic, I mean, the basic non-classical state they can make, but it's not so easy actually, are single photon states. Single photon states are non-classical. And then you try to make 2 photon states and 3 photon states, etc. So these are non-classical. But then the squeeze states I mentioned, they're non-classical. The usual claim to fame of these is that they are instrumental in quantum metrology. You know, in the measurement of gravitational waves, where the signal is very low, squeeze states were used. But squeeze states are Wigner positive. They're P negative, but Wigner positive. See, so that's why I talked about the one question I haven't at all answered, right? Which is a bit related to Jan's question. Anyway, where is it? Here, last one, right? When I say figure of merit, that you have to have some goal in life, and then you have to say, can I do this, reach this goal better with this state and with that one? So if you want to measure gravitational waves, you do it better with a squeeze state than with a coherent state, for example. If you want to build a quantum computer with optics, you need negativity. If you want to ride your bicycle to the store, you don't need any of them. You know, you have to make up some task that will be easier with such or such a state. So that's the.
I see. So are there other questions? Comments? Protests? Okay, doesn't seem
Yeah, I like
so.
protest. No protest. That's too bad.
Okay. Okay, no, I see nowhere, and I see nothing in the chat. Okay, then I think we can finish the official part of the talk. And maybe before stopping the recording, so there will be no seminar in 2 weeks because I hope all of you will be at the International Conference on Mathematical Physics in Strasbourg. I don't think there will be a seminar on the 16th of July, but there will be most likely the last seminar of before the summer will be on July 30 by Robert Wald. Okay, so I think we can stop the recording and yeah, let's stop the recording first.